So before we start worksheet 20, the remaining of the problems, I would like to remind you all about the upcoming final exam. So our final exam is next week, next Wednesday. It's from 10:30 a.m. to 12:30 a.m. Okay, so final exam next Wednesday from 10:30 a.m. to 12:30 p.m. 12:30. So it's comprehensive exam, so it will cover everything from the beginning up to this point. So for the old material, I would recommend you guys to review the 3 tests. Okay, and also review all the worksheets. What do you mean? Tests? You mean the test that we took? Yeah, you mean the keys, test keys? I don't know what. Oh, okay. Are you talking about the?
I thought you meant like the actual test, sorry.
No, sorry, not actual test. The actual test would be in person, just like last time. I may give you guys multiple choice questions on computer. Okay, I may provide you computers. I still need to think about that. But the other part of the problem, the other part of the exam would be in person, just like last time. Okay, I have already posted the keys to the test on Blackboard. Okay, you can check the keys on Blackboard. Also, for the new material, I will post some practice questions sometime tomorrow or on Friday. So practice problems for new material. Will be available. For the multiple choice question part, please review the quizzes. Okay. So the final would be worth 150 points. There would be 10 bonus points. There would be about 15 multiple choice questions, about 1 to 2 short answer questions, and maybe 3 to 5 problems, numerical problems. Okay. I will post all the equations, all the relevant equations on Blackboard sometime this week. Anything else you want to know about final? Okay, so that's about final. Again, just a reminder, it's next week, next Wednesday, 10:30 a.m. to 12:30 p.m. Don't forget that. It's very important. Okay, so let's start worksheet 20. We already completed number 1 and 2. Now let's look at number 3. A spherical shell rolls without slipping. What percentage of its kinetic energy is rotational kinetic energy? And part B, what percent is linear or translational kinetic energy? Yes.
We also didn't finish question 2.
We haven't finished question 2 yet?
We did most of it, we didn't do the
Oh, okay.
total kinetic energy.
Oh, okay. Okay. So let's continue number 2 then. I forgot about that. So we got final angular velocity last time. Now let's look at the kinetic energy, initial and kinetic energy final. So if you remember from linear motion, kinetic energy is given by 1/2 mv squared. This is for translational motion. Now for rotational motion, we'll have a different kinetic energy. So it would be 1/2 mass. The rotational counterpart of mass is moment of inertia, and velocity is angular velocity. So that's the kinetic energy for rotational motion. Okay, and that's what we want to find. So initial kinetic energy before folding the hands is 1/2 I, okay, initial moment of inertia, omega I squared. So 1/2 initial moment of inertia before folding the hands, when the hands are stressed, 13 kg meters squared, and then omega is pi radian per second, okay, squared. So do the calculation. That will give you about 64 joules. So that's initial kinetic energy. And do the same kind of thing for final kinetic energy. So final kinetic energy is 1/2 final moment of inertia times final angular speed squared. So 1/2 when the arms are folded, the moment of inertia is 2.6 kg meters squared. Okay. And omega, what did we get for omega? Do you guys remember?
15.71.
15 point, okay. Or you can also write, that's also 5 pi, okay. So you can write either 5 pi or 15.71. You can just write 5 pi radian per second squared. So do the calculation. That will give you final kinetic energy, which is 320 joules. What's that, sir? Oh, someone is talking outside. So we see here that when the person folds the arms, the person moves faster, rotates faster, okay, compared to when the arms are stressed. And that's what you see in the ice skating. When the ice skaters fold their arms, they spin faster compared to when the arms are stretched out. Okay, so that's number 2. Now, number 3 is similar to this one. It's pretty straightforward once you know the formula. So here we have a spherical shell. Spherical shell is something that is hollow inside, and it is rolling without slipping. So when it's rolling without slipping, it has two types of motion. One is it's moving forward, so it has translational motion. And it's also rotating about its axis, so it also has this rotational motion. So that means we need to separately find the kinetic energy for rotational motion and translational motion. Okay, so the kinetic energy would be sum of the kinetic energy due to rotational motion and kinetic energy due to translational motion. So total kinetic energy is translational kinetic energy plus rotational kinetic energy. So translational kinetic energy, we know the formula for that. It's 1/2 mv squared. Rotational kinetic energy is, we just used that before, so I omega squared. And the shell is rotating without slipping, and the condition for that is rotation without slipping is V is equal to omega r. Okay, so we can either write V in terms of omega or omega in terms of V. So let's write omega in terms of V. And we also need to know moment of inertia for the spherical shell. Okay. So if you look at the table I showed you last time, you can find the moment of inertia for the spherical shell. Not that one. You can also find that from your textbook. So let's see, what's the moment of inertia of spherical shell? Okay, seems like I don't have that here. It's not here. So I think it's, let's see. It's 1/2 mr squared. Okay, you can confirm that from the textbook. So it's 1/2 mr squared if it is rotating about the center. Okay, that's the axis of rotation. So I is 1/2 mr squared. It's same mass, so either you write small case or capital case. So let's just write small case. R is the radius of this sphere. M is the mass. And omega, from this relation, we can write omega is equal to V over R. Okay, so V over R is omega, and square of that. So 1/2 mv squared plus 1/2 and 1/2 is 1/4 m r squared. This is V squared over R squared. Cancel R squared and R squared. So 1/2 mv squared plus 1/4 mv squared. So now we need to add these two terms. So least common denominator is 4, so 2 mv squared plus mv squared. So that would be 3/4 mv squared. Okay, that's the total kinetic energy, Ke total. Now, for part A, what percentage of the total kinetic energy is rotational kinetic energy? Okay, percentage of rotational kinetic energy would be rotational kinetic energy over total kinetic energy times 100%. Okay, that's just finding what percent of this total kinetic energy is this rotational kinetic energy. So rotational kinetic energy is formula for that is 1/2 I omega squared. Since the total kinetic energy is in terms of mv, v, so we want to express this in terms of m and v. So 1/2 I is 1/2 mr squared, and then omega is v over r. Okay. So that's 1/4 r squared and r squared cancel, so mv squared. So rotational kinetic energy is 1/4 mv squared. Total kinetic energy is 3/4 mv squared times 100%. So cancel mv squared and mv squared. You can cancel 4 and 4 also. So that's 1/3 times 100%, which is 33.3%. Okay, so 33.3% of the total kinetic energy is rotational kinetic energy. Now, what percent of total kinetic energy is linear kinetic energy? You can either subtract 100 from that, or you can just find using the formula. So percent of translational Ke is translational Ke over total Ke. So translational kinetic energy is 1/2 mv squared, and total kinetic energy is 3/4 mv squared. So cancel that. So what's left? Cancel this one and this one with 2 remaining on the bottom. So 2/3, 2/3 times 100%, which will give you 66.6%. Okay, so adding these two will give you 100%. Okay, so that's number 3. Now let's look at number 4. So there is a inclined surface, and you roll a solid ball or a solid sphere along that inclined surface. So the inclined surface is 30 centimeters high. So when you release this, you will need to find what would be the speed of the ball at the bottom of the inclined surface. So we want to find V final. Okay, consider you started from rest, so V initial would be 0. We need to find the V final. And that's all information we have. I mean, this problem could be solved using kinematics. Okay, using v final equal to v initial plus at and other things, but we cannot use kinematics here because we don't have enough information. But fortunately, this kind of problem could also be solved using energy principle, okay, conservation of energy. So if we use conservation of energy, we won't need much information. So conservation of energy is total energy at this point would be equal to total energy at that point. Energy is conserved, okay? Considering that there is no loss of energy. Okay, so let's say this point is 2, this point is 1. So potential energy at 1 plus kinetic energy at 1 is equal to potential energy at 2 plus kinetic energy at 2. Since the ball is rolling, that means we have two types of kinetic energy here, not just one. Okay? So here this has Ke translational plus Ke rotational part. Same thing here. Ke translational plus Ke rotational. But this term would be 0 in the beginning because it starts from rest, so we don't need to worry about this kinetic energy at point 1. All we have at point 1 is potential energy, and potential energy is given by m, g, and h. So that is equal to potential energy at the bottom would be 0 because the height is 0. Now here, this ball will have part translational kinetic energy and part rotational kinetic energy. So 1/2 translational is mv squared and rotational is 1/2 I omega squared. Again, this ball is rotating while it's rolling down, it's rotating without slipping. So that means V is omega r, or omega is V over r. And for a sphere, the moment of inertia, you can check that from textbook. The moment of inertia for a sphere is, it's not a hollow sphere. Okay, for hollow sphere, it's 1/2 mv squared. For hollow sphere, it was 1/2 mr squared. But this is a solid sphere. For solid sphere, it's is 2/5 mr squared. Okay. So mgh is equal to 1/2 mv squared plus 1/2 I for solid sphere is 2/5 mr squared, and for rolling without slipping, omega is V over r squared. Okay, so let's simplify this. mgh is equal to 1/2 mv squared plus 1/2 2/5 mr squared v squared over r squared. Cancel r squared and r squared. And all these terms have m. So you can cancel m from all the terms. This m, and that one cancel. So what's left on the left side is gh. Right side we have 1/2 v squared. By the way, here this v is final velocity. Okay, I didn't write vf here. If you want, you can write final velocity, but just understand that v is final velocity. We didn't have initial velocity, so if you have v, that means it's final velocity. So 1/2 v squared plus 2 and 2 cancel. So 1/5. What's left here? We have v squared left. Okay. So GH, the least common denominator here is 10. So 5v squared plus 2v squared. Okay. That's 7v squared over 10. Now here we want to find v squared, so you want to write this in terms of v squared. So multiply both sides by 10. Actually multiply by 7/10 because I want to get rid of 7/10 on this side. So multiply by 10 over 7 I mean. So 7 and 7 cancel, 10 and 10 cancel. So 10 over 7 GH is equal to v squared. So v is 10 over 7 GH square root. Okay. So 10 over 7, G is 9.8 meters per second squared. Height of the ball initially is 30 centimeters. In terms of meters, it would be 0.3 meters. Okay, so that will give you the final velocity. I don't have the answer, so why don't you guys do the calculation and tell me the answer. So 2.05. Okay. So 2.05 meters per second is the final velocity. Okay. So that's number 4. Now let's look at number 5, last one. So you're rolling a bunch of objects from an inclined surface, and you want to decide which object rolls down the incline fastest. Okay. So it's a similar kind of problem. So you just need to find the velocity for each of the objects at the bottom. So what you can do is, let me just show you a general way to do this one. So you can do the problem 4 times like before, but you can also do this in a general way. Okay? So we know the energy at the top here would be equal to energy at the bottom from conservation of energy. Okay. So at the top we have only potential energy because it starts from rest. So we have potential energy. Let's also write kinetic energy, but that would be 0. And energy at the bottom would be potential energy plus kinetic energy, but this would be 0 at the bottom. Okay, so potential energy is mgh. Kinetic energy is sum of rotational kinetic energy and translational kinetic energy. And for rotation without slipping, omega is V over R. plus 1/2 mv squared. So the idea here is we want to get an expression for v, okay? Because we want to find the velocity or speed at the bottom. So let's simplify this. So this would be 1/2 I v squared over r squared plus 1/2 mv squared. So pull this v squared outside the parentheses. And if you want, you can also pull this 1/2 out. It's common. So I over r squared is remained in first term. And then here, what's remaining is m. So I pull this 1/2 and v squared outside the parentheses because they are common. Now, in order to get the expression for v, let's divide both sides by this, okay? So mgh, divide that by 1/2 I over r squared plus m I 1/2 I over r squared plus m, divide that by 1/2 I r squared plus m. Okay. Again, all I'm doing here is dividing both sides by this term so that I can cancel that. So what we have here is v squared is equal to, this 2 will go up, so we have 2 mgh over I over r squared plus m. So our aim here is to get expression for v. So 2 mgh I over r squared plus m. So that's the general expression for the speed at the bottom. Now you need to find that for each of the objects. Okay, so we have 4 different objects. The first one is sphere. I for a solid sphere. I is 2/5 mr squared. So with that, velocity would be 2 mgh over, replace that I by that 2/5 mr squared. And then on the bottom we still have r squared plus m. Okay. So cancel r squared and r squared. So what's left here? 2 mgh over 2/5 m plus m. So 2 mgh, 2/5 m plus m. What would that be? So 2/5 m plus m. Yeah, it's 7/5 m. So 7/5 m. Cancel m and m. So you take this 5 up, 10 over 7 gh, which is exactly the same as the one we got in the previous problem. Okay, this is just redoing the same thing. Now you find that we already got that answer before. So in the previous problem we got 2.05, I think. So we got 2.05 meters per second. So that's for the solid sphere. Now you do exactly the same thing for a hoop. Okay, a hoop, it's a cylindrical, hollow cylindrical object. So the moment of inertia for that is mr squared. So you guys may be wondering where I got these expressions for moment of inertia. So they are all on textbook. Okay, You don't have to memorize that. You will be provided the formulas in exam if you get any question about this kind of problems. So let's do that for a hoop. So V is equal to 2mgh. Now, the general expression, look at the general expression for V. So that's the general expression for V, 2mgh I r squared m. So okay, that's the general expression. Now you need to use the moment of inertia. So I is mr squared. You can cancel r squared and r squared. So 2mgh over m and m is 2m. So you can cancel 2m and 2m. So what's left is gh. So g is 9.8 meters per second squared. Oh, by the way, height is not given, but since height is same, so let's just assume that it's 30 centimeters, okay? You can just assume any height because it's all same, because we want to get a number. So just like before, because here I assumed this height to be 0.3 meters, so let's also assume the same height here. But if you want, you can also consider any other number. So 0.3 meter. So find that. That will give you the speed for the hoop. And you do the same thing for the other objects, okay? So a solid cylinder. I will let you guys complete this problem. I'll just give you the moment of inertia for the other objects, and I will not do this, so you guys can do that. Say for a solid cylinder, I is mr squared over 2, and for a hollow sphere, we already saw that before, I is 2/3 mr squared. Okay, so find V for this, find V for this, and then compare all the speeds and see which one would be fastest at the bottom. So that's worksheet 20. And that would be the last worksheet. There's one more chapter we want to talk very briefly because we want to do a lab on that. So let's briefly talk about that. The last chapter we want to talk here is simple harmonic motion. So consider a spherical bowl like this one and a marble. So when you don't disturb this marble, it will just stay at the bottom, okay? And this position where it stays without any movement is called equilibrium position. Okay? Equilibrium position is where it will be at rest and it's stable. But if you disturb it slightly, if you move it either to the left or to the right, push to the left or to the right, there would be this weight of this object, and the weight of this object will have this component which will restore it to its original state. Okay? It will pull this object down because of this net force. Okay? And this net force is nothing but it's only a part of this weight. So this weight at this point, let's draw a separate picture here. So that's the ball at that point. So that's the weight. This weight has this component. Okay, assume that it's not that long for some reason. So and this component. So this W sine theta, this component pulls this object back to its original state. Okay? So this is the restoring force. It tries to restore the object to its equilibrium. And while it goes back to its equilibrium, it doesn't stop at that point. Okay, it'll go to the right, and when it moves to the right, there will be this restoring force again that tries to restore it back to the equilibrium. And as it falls, again it goes to the left. Okay, that continues forever, unless you stop that with some kind of force. In real practice, we have friction. That's why the object will eventually stop. In this case, let's say it's a marble or a ball. It stops eventually. But if you remove the friction, then it will do this back and forth motion all the time. Okay, forever. And this kind of back and forth motion is what we called oscillation. Okay? And in physics, it's also called simple harmonic motion. So we term this kind of motion as simple harmonic motion. In short form is SHM. And any kind of simple harmonic motion is characterized by period and frequency. Okay. So period is like if you start from this point, it goes to this point, and then back again to the same point, and then to the left, and then back again. Okay? So the time for one complete oscillation, starting from here to the right, back again to the equilibrium, and to the left, and back again to the equilibrium, the time for that is called time period. Okay? Time for one complete oscillation. And frequency is how many such oscillations an object completes in 1 second. Okay, so frequency is number of complete oscillations in 1 second. So if you look at any kind of graph that has a periodic motion, for example, here, this is the signal of the heartbeat. This is kind of a periodic motion, periodic beating. You see same kind of shape in certain period of time. Okay. You have a peak here, another peak here, another peak here. So this the time from one peak to another peak is what we call period. Okay, from here to here is also a period. Okay, and frequency is how many such complete oscillations are completed in 1 second, and the relationship between time period and frequency is time period is 1/f. Okay, they are reciprocal to each other. time period is measured in seconds. It's a time, so it's measured in seconds. And frequency is measured in, you guys know what that unit is? You might have heard about that. Yes, exactly. So it's hertz. Okay. Which is oscillations per second. So let's look at some questions. Okay. So a mass oscillates on a horizontal spring, so the mass is moving back and forth to the right and left from its equilibrium position. Let's say the spring in its normal state is like that. Okay, you pull this spring to the right and then let go. It will do this back and forth about that equilibrium position. Okay. So the period for one complete oscillation is 2 seconds. Then what is the frequency? It's pretty straightforward. So we know frequency and period are reciprocal to each other. So F is 1 over T. So take the reciprocal of 2 seconds, which is 0.5 hertz. Here, if the mass is pulled to the right and then released, how long will it take for the mass to reach the leftmost point of its motion? So, what do you guys think is the answer? So think about one oscillation. One oscillation is, so if you start from here, it will go back to its equilibrium, and then to the left, and then to the right, and then back again to that point. So from here to here, from here to here, and then back here, and then back here. That's T. Here the question is, how long does it take to get from here to here? Is that half of capital T? Oops, what happened? That's half of capital T, right? Capital T is from here, again here to equilibrium, equilibrium to left, and then back to equilibrium, and then back to where it started. So that's capital T. But here we want to find from here to here, and then from here to here, okay, that time, which is half of that. Okay. So let's see how much time we have. 2 minutes left. Okay, just this is the last question. Okay, a typical earthquake produces vertical oscillation. So the land oscillates during the earthquake vertically, and sometimes it also oscillates horizontally. But here we are talking about vertical oscillation. Suppose a particular quake oscillates the ground at a frequency of 0.15 hertz. As the earth moves up and down, what time elapses between the highest point of the motion and the lowest point? So, highest point to the lowest point. So if you consider highest point and then to the equilibrium, okay, normal state, and then to the lowest point, and then back to the normal state, and then back to the highest point, that's capital T. But here, we are only considering from highest to the lowest, which is half of capital T. So we want to find T over 2 here. So let's first find T, and then we can divide that by 2. Okay? So T would be 1 over F. F is that 0.15, and then what we want to find here is T over 2. Oops. Okay. So that's oscillation. We'll continue this in the next lecture, and today we'll also do lab on this. So that's all for this lecture.